Hi students, good morning. Hi, how are you? This is Kishore, working as physics lecturer at Vigyan College. So we are dealing the chapter Mechanical Properties of Solids. So in this chapter, in the last section, we discussed the modulus of velocity and types of modulus of velocity. So there are three types of modulus of velocity: Young's modulus of velocity, rigidity modulus of velocity, and bulk modulus of velocity. So we all discussed in the last section, and I have also discussed the what is Poisson's ratio and what are the theoretical values and practical values of Poisson's ratio. And now in this session, we will discuss how the wire behaves whenever we increase the loads. So we are taking a wire, so one end of the wire is fixed, whereas the other end the loads are increased. So how the wire behaves whenever we increase the loads. So let us go to the session. So now let us see the behavior of wire. So here we are doing, so one end we are taking a wire. So one end of the wire is fixed to the rigid support, whereas the other end the loads are gradually increases. And by loads increasing gradually, we are drawing a graph by taking stress on y-axis and strain on x-axis. So this kind of graph is called a stress strain graph, or it is also called as a stress strain curve. So let us take a wire. So we are taking a wire. So one end of the wire is fixed to the rigid support. So this is the rigid support. So one end of the wire is fixed to the rigid support, whereas at the other end the loads are added. So here we are adding the loads. So this is the rigid support. So one end of the wire is fixed to the rigid support, whereas the other end the loads are added. So by gradually increasing the loads, so obviously there is a change in the length of the wire. So whenever we increase the stress is nothing but force by area. So force is nothing but mg, so loads. So by gradually increasing the loads, we are increasing the stress. So thereby there is an increase in length of the wire. So strain is nothing but increase in length by original length. So whenever we increase the stress on the wire, definitely there is an increase in the strain on the wire. So we are drawing a graph by taking strain on x-axis and stress on y-axis. So that kind of graph is called as stress strain graph. So okay, so we are taking a wire. So one end of the wire is fixed to the rigid support, whereas the other end the loads are added. So by gradually increasing the loads, we are drawing a graph between stress and strain, or in other words, we are drawing a graph between loads and extension. So that is M and E. So M is nothing but mass, whereas E is nothing but elongation. So in other words, the graph is between stress and strain, so which is called as the stress strain graph. So the graph is, so we are drawing a graph by taking, so this is x-axis and this is y-axis. So we are taking strain on x-axis and stress on y-axis. And the graph is, let us consider this point as origin. So this is the point A. So here we get, this is the point B, and this is C. So we are drawing a graph by taking strain on x-axis and stress on y-axis. So the graph is as shown in the diagram. So this is the point A, and up to B this is the shape of the graph, and from B to C this is the shape, and this is from C to D, and then it is from D to E. So let us consider this point as E. So this is a graph between strain and stress. So this graph is called as stress strain graph, or it is also called as stress strain curve. So by seeing this graph, we can explain the behavior of a wire. So let us see, up to the point A, it is a straight line. So which indicates that, so with the increase of stress, there is an equal increase in strain. That means Hooke's law is obeyed. So up to the point A, the graph is a straight line, which indicates that stress is proportional to strain. So that's why the point is called as the proportionality limit. So this is the first thing. So up to the point A, the graph is a straight line, which indicates that stress is proportional to strain. That means the Hooke's law is obeyed. So that's why the point A is called as the proportionality limit. And beyond the point A, there is no proportionality. That is, stress is not proportional to strain, but still the wire has elastic nature. So why you can say that the wire has elastic nature? So if we remove the loads whatever we added at the point B, the wire once again get back to the same original length along this path only. So that's why the point is called as the elastic limit. So the point B is called as the elastic limit. So the A is nothing but proportional limit, the point B is elastic limit. So beyond the point A, so even though there is no proportionality valid, that is stress is not proportional to strain, but still the wire has elastic nature up to the point B. So that's why the point B is nothing but elastic limit. And beyond the point B, so if we increase the strain, so there is a stress also increases, but here the wire does not have elastic nature. So how you can say that the wire does not have elastic nature? So if we remove the loads at the point C, then the wire does not get back to its original shape, but it reaches some other point. So let us consider this as O dash. So this is nothing but increasing length. So beyond the point B, if we increase the strain, the stress also increases, but the wire does not have elastic nature because so it comes to some other point. So that means the point C is called as the permanent set. So what is permanent set? So permanent set is nothing but whenever the loads are added, so the wire does not have elastic nature. That means there is a permanent increase in length of the wire, which is called as the permanent set. Now let us see the graph. So beyond the point C, so even though we should not increase the stress, the strain increases more rapidly. See the graph here. So it is a more peak we are observing here. So even though we don't increase the stress, the strain increases more rapidly. That means the wire gets yielding starts at the point D. So that's why that point is called as the yielding point, or it is also called as the fracture point. Yielding point, whereas the stress corresponding at this point is called as the ultimate tensile stress, or it is also called as yielding stress. Okay, so beyond the point C, even though we increase or with a small increase of stress, the strain increases more rapidly. That means the yielding starts at the point D. So that point is called as the yielding point, and the stress corresponding is called as ultimate tensile stress. And beyond the point B, so the wire becomes thinner and thinner. That means the area of cross section of the wire decreases, and finally at the point E, the wire breaks. So that point is called as the breaking point. So beyond the point D, so the wire becomes thinner and thinner. That means the area of cross section of the wire decreases, and the wire finally breaks at the point E. So that point is called as the breaking point. So these are the conclusions drawn from this graph. So by observing these graphs, that is a strain stress graph or stress strain graph, so we are getting the proportional limit, elastic limit, permanent set, yielding point and breaking point. So watch this video here. So instead of wire, we are taking here a spring. So one end of the spring is fixed to the rigid support, whereas the other end the loads are added, and the loads are gradually increasing. So by gradually increasing the loads, a graph is drawn by taking strain on x-axis and stress on y-axis. So that graph is called as the stress strain graph. Got it? So we are taking a spring here. So one end of the spring is fixed to the rigid support, whereas the other end the loads are added. So by gradually increasing the loads, we are drawing a graph between strain on x-axis and stress on y-axis. So that graph is called as the stress strain graph. And we observe some conclusion from the graph just now. So they are nothing but the proportionality limit, elastic limit, and permanent set, and yielding point or ultimate tensile strength, and breaking point or fracture point. So now let us see about these definitions clearly. So just now have seen the graph between stress and strain. So strain is taken on x-axis and stress is taken on y-axis. And the graph is a straight line up to the point A. So watch this video also. So up to the point A, the graph shows a straight line. So which indicates that up to the point A, the stress is proportional to strain. So which is nothing but Hooke's law. So Hooke's law is nothing but stress proportional to strain for small deformation. So the maximum stress up to which stress is proportional to strain, and Hooke's law obeyed is called as the proportionality limit. So that is about the proportionality limit. So in the graph up to the point indicates a straight line. So which indicates that the stress is proportional to strain and Hooke's law is obeyed. So that point is called as a proportional limit. So the maximum stress up to which stress is proportional to strain and Hooke's law is obeyed is called as a proportionality limit. So as we are observing here the definition. And coming to the beyond the point A. So even though we are increasing the stress and the strain also increases, but up to the point A, it has Hooke's law is obeyed. That means stress is proportional to strain. But beyond the point A, the stress is not proportional to strain. That means Hooke's law is now obeyed. But still the wire has elastic nature. So how you can get that the wire has elastic nature? So if you remove the loads, then the wire once again get back to its original length. That means the wire has elastic nature. So up to the point B, the wire has elastic nature. So that's why that is called as elastic limit. So what is elastic limit? The maximum stress up to which the wire has elastic limit is called as the elastic limit. The maximum stress up to which the wire has elastic nature is called elastic limit. And now let us see what happens beyond the point B. So beyond the point B also, we are increasing the stress, thereby strain also increases. And up to the point B, the wire has elastic nature. But now the point does not have elastic nature. That means it becomes the plastic nature. That means, so how we know that? So if we remove the loads at the point C, so the wire does not get back to original length, but there is a permanently increasing length of the wire. So that's why that point is called as a permanent set. The maximum stress up to which the length of the wire increases permanently is called as a permanent set. So see once again, the maximum stress up to which the length of the wire increases permanently is called as the permanent set. So let us see, recap once again the conclusion drawn here up to the point C. So the first one is proportional limit. The maximum stress up to which stress is proportional to strain and Hooke's law is obeyed is called as a proportional limit. Whereas the maximum stress up to which the wire has elastic nature is called as elastic limit. Whereas the maximum stress up to which the length of the wire increases permanently is called as the permanent. So what happens beyond the point C? So here also, whenever we increase or without increasing the stress, the strain increases more rapidly. That means the length of the wire increases more rapidly. That means the area of cross section decreases and the yielding starts. That means the strain increases more rapidly and irregularly. So that point is called as yielding point. Then what is yielding point? So the maximum stress up to which there is a irregular increase in strain just to start is called as yielding point. The maximum stress up to which there is a irregular increase in strain just to start is called as yielding point, or the stress corresponding at this point is called as yielding strain, or it may also called as ultimate tensile strength. So the maximum stress up to which where there is a irregular increase in strain just to start is called as the yielding point. So beyond the point D, the wire becomes thinner and thinner because of area of cross section decreases, and finally the wire breaks at the point E. So that point is called as the breaking point, or it is also called as fracture point, whereas stress corresponding at this point is called as the breaking point. The maximum stress up to which the wire breaks is called as the breaking point or fracture point, whereas the stress corresponding to the breaking point is called as the breaking stress. So these are conclusions drawn from the graph. So we are seeing the 5 definitions: the proportional limit, elastic limit, permanent set, yielding point, and breaking point. Now let us see what is ductile metals and what is brittle metals. So the metals which can be drawn into thin wires is called as ductile metal. So these are the uses of stress strain graph. So what are the uses of stress strain graph? Why you are going to study the stress strain curve? So these are the uses. So metals which can be drawn into thin wires is called as the ductile metals. So examples for ductile metals are gold and silver. Whereas the metal which cannot be drawn into thin wires is called as a brittle metal. The examples are glass and ceramic. So what is ductile metals? That means if there is a large gap between D and E, so that kind of metals are called as ductile metals. That means the wire does not break immediately after crossing the elastic limit. So that kind of metals are called as ductile metal. And if the wire breaks immediately after crossing the elastic limit, or the range is very less, that kind of metals is called as brittle metals. So brittle metals are those which cannot be drawn into thin wires, whereas the ductile metals are the metals which can be drawn into thin wires are called as ductile metals. So these are the uses of stress strain curve, and the stress strain behavior is different for different metals. That means it varies from one material to another material. So if you take steel, the stress strain curve is some other shape, whereas if you take the rubber, the stress strain curve is different. That means the stress strain behavior varies from one material to other material. So here we are showing the graph. So that graph shows the rubber can be pulled into several times to its original length and still return to its original shape. That means you expand this rubber. So even though there is an increased length of the wire, whenever we apply force on the body, so when we remove the force,
which can be
then
stretched
the rubber
to cause
gets back to its
large
original shape.
strains
That means
are
the rubber
called
can be pulled to several times
elastomers.
to its original
Interestingly,
length and still
the
returns to
elastic
its original
tissue
shape.
of aorta
So
present in our
stress
heart
strain behavior
is
varies
also
from
an
material to
elastomer.
material.
Let's recap. The
So what
stress
can we
strain
observe from
curve
stress
varies
strain
from
graph
material.
is nothing but, so up to some region the wire has elastic nature, that is up to the point B the wire has elastic nature, and beyond the point B the wire loses its elastic nature and gets to plastic nature. So from the point B to E, so the wire has plastic nature, whereas up to the point B the wire has elastic nature. So we can say that from this graph we can say that, so in which region the wire behaves as elastic nature and in which region the wire has plastic nature. So the elastic region is very large, the material does not obey Hooke's law over most of the regions. So the elastic region is very large, that means the material does not obey Hooke's law over most of the region. There is no well-defined plastic region, so that also changes from material to material or substance to substance. So substance like tissue of aorta and rubber etc., which can be structured to cause large strain are called as elastomers. So what is elastomers? So there is no well-defined plastic region. So some substances like tissue of aorta and rubber etc. can be stretched to cause large strains called as elastomers. So which can be stretched to cause large strains are called as elastomers. So which are nothing but tissue of aorta and rubber. So these material behaves like a elastomers. So what are the uses of stress strain graph is nothing but, so you can say up to the which point the wire has elastic nature and up to which the wire has plastic nature, and from this only you can get which material is ductile metal and which material is brittle metal. Students, in this session we will learn about behavior of wire. So behavior of wire is nothing but one end by taking a one wire. So one end of wire is fixed to the rigid support, whereas the other end is loads are added, and gradually increasing the loads we are drawing a graph between stress and strain, which is called as stress strain graph or stress strain graph curve, and we observe from the graph some conclusions. So what is proportional limit, elastic limit, permanent set, yielding point and breaking point. And also we have seen the uses of stress strain graph. That means up to some region the wire has elastic nature, and beyond that point the wire behaves like a plastic body. So what are the uses of stress strain graph? That is ductile metal and brittle metals. And what are elastomers? That is discussed in this session. So we'll meet in the next session. Up to then, have a great day. See you again. Thank you.